This video offers some help and hints with Problem 2-23 from the end of Chapter 2 in the 9th edition of Harris's Quantitative Chemical Analysis textbook. So this question has 3 parts, and I'm going to present this video in 2 parts. The first part, I'm going to present some sort of general guidelines and hints, and then I would advise you to pause this video and go try and work the problem on your own. After that, you can come back and restart it, and I'll go through and walk you through how you might go about solving this problem. So this problem there's a little more text in it than I've written down here, but it asks how much of the primary standard grade benzoic acid, which has a formula mass of 122.12 grams per mole and a density of 1.27 grams per milliliter, should you weigh out to get 100 micromolar aqueous solution in a volume of 250 mLs. So that's our first question. Part B is what would be the apparent mass of the benzoic acid that you would weigh out? So what would the balance read if you actually wanted to get the mass that you calculate in Part A? And finally, we're given a selection of some glassware that we could use to take that 100 millimolar solution and dilute it down using serial dilution procedures to give us a 500 micromolar solution. So how would we do that? All right, so let's start off with Part A. So Part A is a fairly standard kind of problem, so we want to calculate how much of a solid we would need to weigh out to make 250 milliliters of a 100.0 millimolar solution. So just a reminder, 100 millimolar means that we're going to have 100, and milli, that prefix milli means times 10 to the negative third, and then capital M, molar, means moles, and in this case we're talking about the solute benzoic acid, which I'll abbreviate BA. So we need 100 times 10 to the negative third moles of BA, benzoic acid, in every 1 liter of solution. So that's what that capital M means. Stands for molarity, which is moles divided by liters. Okay, so we've got that part. And then what we're trying to do is figure out if we have 250 milliliters of this solution, how many grams would you need of this benzoic acid? And so the procedure is we can use volume, or here's the hint. This is a pretty big hint. So we can start with our volume that we have, the 250 milliliters, use molarity then as a conversion factor to figure out moles of benzoic acid. And then we can convert using the formula mass, the formula weight, molar mass, to figure out grams of benzoic acid. And so that should tell you how much you need to weigh. So for Part B, what it's asking us to do is calculate the apparent mass. And so if you actually wanted this number of grams of benzoic acid, what would the scale read? Now you might think it would be the same number, but remember there's this buoyancy effect. So things, when we weigh them in air, weigh a little bit less because of their displacement in air, and it kind of depends on how it compares to the density of the calibration weight that we use to calibrate the balance. And so there's an equation for that that says the actual mass is equal to the apparent mass, m prime, times 1 minus the density of air divided by the density of the calibration weight, and then we divide this whole thing by the quantity 1 minus, again, the density of air, that divided by the density of the substance that you're weighing. Alright, so in order to use this equation, we know what actual mass we want, so I'm going to put a check mark over that. That's this mass that we calculated in Part A. We're trying to find the apparent mass, so I'm going to put a question mark there. Then you're going to need to look up these densities. So the density of the weight, standard weights, are usually 8 grams per milliliter. The density of air under atmospheric pressure, normal atmospheric pressure, and around room temperature is usually, and well, you can look that up, but I'll let you look that up. And then the density of the substance, that's the density of benzoic acid, and that was given to us in the question. So you'll want to rearrange this equation to see if you can solve for the apparent mass m prime. Finally, Part C, we're given some various pieces of glassware. So we're told we have volumetric flasks in the sizes 100, 250, 500, and 1,000 milliliters. and that we have volumetric transfer pipettes in the volumes 5 and 10 milliliters. And so what we're going to do is a serial dilution. So we're going to start with our 100 millimolar solution, and then we're going to, in a couple of steps, we're going to dilute that down to another solution. Then we're going to take some of that and dilute it down again, and maybe we have to keep doing this. So that's what we call serial dilution. So you're going to take some of this solution, add a little bit of it into your volumetric flask, and dilute the rest with water. And you're going to keep on doing that. So that's a serial dilution procedure. So each time we dilute our sample, we decrease the concentration by a certain factor. So for example, if I take 10 milliliters of my 100 millimolar solution and add that to a flask, a 1,000 milliliter flask, and then dilute that with water, then I can calculate what my new molarity is just using the dilution equation here. So this will tell me that my new concentration, so solving for question mark molarity, is going to be 10 divided by 10 times 10 divided by 1,000 times 100.0 millimolar. And so I have canceled out the milliliter units that were here next to the 10 and the 1,000 when I've divided through by 1,000. All right, so this bit right here, that's called the dilution factor, and it tells you how many times dilute your solution is. So notice I can reduce this fraction by canceling off the zeros here, and this is 1/100th. So our solution is going to be 1/100th the concentration that it was previously. So 1/100th is 10 to the minus 2. So what you might want to do, the hint, is to figure out how dilute the solution is compared to the initial solution. So we want 550 micromolar. And so how many times more dilute is that compared to 100 millimolar? All right, so we've got a mismatch in units here, so we're going to need to convert those. And so we want to look at this ratio. And then we're going to need the same ratio in volumes, but we're going to need a couple of them together, so you won't be able to do it in one step. So you're going to get a dilution factor for step 1. And so, for example, that might be the 10 milliliters into 1,000 milliliters. And you want to get that to equal this change in dilution, right? And then we might need another dilution factor for step 2 or step 3 and so on. And we just multiply those together. So step 2, maybe we want to take the 5 mil pipette, for example, and dilute it to some different volume that we need to figure out. So you might want to try by trial and error figuring out what combination is going to give you this dilution factor. So for example, here we figured out that our dilution factor was 10 to the minus 2. How much dilution do you need? So what is this? 10 to the minus what? And what combination of steps multiplied together will give you that same dilution factor? So see if you can figure that out from those hints. So go ahead and pause the video now, and I'll be right back, and then we can talk about how you would work this problem. Okay, so now let's give this a try. So we're going to follow that procedure that I talked about for part A. So let's work part A first. So we've got 250 milliliters as our volume. And we're going to want to convert that to liters. And so I'm just going to do that by moving the decimal place by 3. So that's the same as 0.250. That's what you would get if you divided by 1,000. So that's 0.250 liters. And we're going to use molarity now to convert that into moles. So we've got 0.250 liters times our molarity, which is 100.0 times 10 to the negative third moles of benzoic acid per liter of solution. So my liters cancel out. And then I'm going to use the molar mass of benzoic acid that was given to me in the problem. That's 122.12 grams of benzoic acid per mole. And so the mole unit will cancel out. And now I'm left with the final answer, which is how many grams of benzoic acid I should weigh out. And I calculated a value of 3.053 grams. All right, so that's the actual mass that we would need, but because of buoyancy, the balance won't read exactly that if we want that number of grams, and so let's figure out how to do that. So that equation that I wrote down previously, we want to solve that for m prime, and then substitute in all of the values. So m prime is equal to the actual mass that we want, so that's 3.053 grams, times, and then 1 minus the density of air, which is 0.0012 grams per milliliter. That's the value that's in your textbook. We're going to divide that then by the gram of the density of the sample. So benzoic acid has a density of 1.27 grams per milliliter. Close that parentheses. And we divide that whole mess by 1 minus the density of air, 0.0012 grams per milliliter, divided by the density of the calibration weight, which is 8 grams per milliliter. Notice that these two parentheses have switched places from my original equation. That's because I solved that equation for m prime. So remember that m was over here and m prime was over here, but they've exchanged places when I go to solve that. So you have to punch this into your calculator very carefully. I use parentheses, so I open a parentheses here in my calculator and I type 1 minus, and then I put another parentheses in here for this division, and I close the parentheses. And I do the same thing down here. So there's another inner parentheses here when I type this all into my calculator. And when you do that, you'll come up with 3.051. So if you wanted to actually weigh out 3.053 grams of benzoic acid, then your balance should read 3.051 grams when you go to weigh it out. So finally, let's look at this question C. So this serial dilution. So we want to compare how much more dilute is 50 micromolar than 100 micromolar. And so I'm going to take 50 micromolar, so that's the same as 50 micro, means 10 to the power minus 6. So I replace the micro with 10 to the power minus 6 molar. And I'm going to divide that by the molarity of my more concentrated stock solution. So 100 times 10 to the negative third, I replace the milli with times 10 to the negative third molar. My molar cancels out, and that gives me as my final result 5 times 10 to the minus fourth. So that's my dilution factor. My solution is diluted by 5/10,000ths of what it was initially. So I need to select a process that will give me that same ratio. All right, so let's look at that. So my first step, I had proposed that before, was that we take 10 milliliters with our 10 milliliter volumetric pipette, and we dilute that to a volume of 1,000 milliliters. And so I told you that that was a 1 in 100 times more dilute, so that's a dilution factor of 10 to the minus 2. So this parentheses, when you divide it out, is 10 to the minus 2. So I need to get times 10 to the minus 4, so another times 10 to the minus 2 would do that, but I also need to get this 5 here. So in this case, I'm going to use 5 milliliters, right? And then I need to dilute that by another 100 times. So that's going to be 5 in 100 milliliters. And so that's going to be, and so 5 divided by 100 is going to give us that, so this is going to be 5 divided by 10 to the second. And so over here I've got 10 to the minus second, and so when I bring that up to the denominator, I get 10 to the, up to the numerator, excuse me. When I multiply these together, it looks like this. Now let's start off with the first parentheses, 10 to the minus 2. And then that multiplies 5. And then I've got the 10 to the power 2 down here in the denominator. So you'll remember that if I have 1 over 10 to the power 2, that's the same as 10 to the power negative 2. So I'm just going to bring that back up here, 10 to the power negative 2. And when I multiply all that together, 10 to the power negative 2 and 10 to the power negative 2, I just add the exponents. So negative 2 and negative 2 is negative 4. And so I end up with 5, oops, let me write that so you can see it, 5 times 10 to the negative fourth. And so that's exactly the dilution factor that I want. So here's my procedure. Take 10 milliliters of the 100 millimolar solution, and add that to a 1,000 milliliter volumetric flask, dilute to volume. Then take 5 milliliters of that solution out, add it to a 100 milliliter volumetric flask, and dilute that flask to volume. When you're done with that solution, you will have a 50 micromolar solution. So that's how we do serial dilutions. It's very useful because it might be very hard to weigh out a tiny amount of benzoic acid, or you'd have to make a huge volume of the solution in order to make a solution that was that dilute. So oftentimes we will make a more concentrated stock solution and then dilute that down serially to come up with the concentration that we want.